Hey guys, it's Chili here, coming back at you with another episode of 3D Fundamentals, tutorial 17. Today's lesson is going to be on per pixel lighting, also sometimes referred to as Phong shading or Blinn Phong shading, although those things include other concepts that we're not going to be talking about today, but doesn't matter. Who cares? Look at this image, look at this picture. I showed you this in the last video, and I said, do you find anything wrong with this? Because I indeed find something incredibly wrong with this. This is a lot of bullshit. Why? Well, take a look at this image. So here we've got a point light source against a plane. All right, this is what you should expect. You should expect that the points on the plane that are very close to the light source here are brighter than the ones that are farther away, for two reasons. First of all, the points are closer, the distance is less, and so the attenuation is less. Reason number two is the angle. The points around here are, the photons are hitting them at about 90 degrees, pi over 2. Whereas the points over here are just getting a glancing blow from the photons. So those two reasons mean we should be expecting this kind of circular lighting pattern, but we're not getting that. We're getting this, which is just flat gray. Now, if I tilt this guy, you can see we can get a kind of a gradient from the bottom to the top here, but that's still not what we're looking for. So why is it that we're getting this pattern in the first place? As usual, we're going to diagram this out in 2D because you don't want to see my 3D diagrams. So we've got a plane, we got a light source. All right, now we're doing per vertex lighting. So for this 2D plane, which is a line, we got two vertices. And so we're going to calculate the color at these two vertices. How do we do it? Well, we use the angle plus the distance because this is a point line. And what do we notice here? Well, we notice that these two angles are the same. And these two distances are the same, so we're going to get the same intensity at both of these vertices, 0.5, 0.5. And then when we interpolate that across the surface of our primitive that we're rendering, well, if you interpolate between the same two values anywhere on this line, it's always going to be 0.5. And so you're going to get a flat color. You're not going to get... You're losing the information, basically, that the angles are approaching. They're going to get closer. They're going to get, they're going to get more closer to 90 degrees, and then they're going to go farther away again. But you don't get that information with this interpolation. It just says, oh, 0.5 intensity here, 0.5 intensity here, 0.5 across the board. Done. Easy. So this is no good. This is a place where per vertex lighting is going to kick us in the balls. Now, how do we solve this problem? Well, one way we could solve it is we could break this up. So instead of having two vertices for this plane, we could make lots of vertices, and then we calculate from here to here and here to here and here to here, and then you're going to get different values. And you're going to get like a 1 in here, and then maybe here you're going to get like a 0.75. And then your interpolation will work, and you'll get a decent looking result. Let's see how that looks. So in game.cpp, I've changed the first scene here, the one with the plane, and I have made it so that I tessellate the plane at a tessellation of 16. So now instead of having two triangles, it's going to have way more triangles. I don't know how many it's going to be. I'm going to guess probably close to 500 triangles. And with that tessellation, now you see we get a good looking result. Here in the middle, we've got this round sort of lighting effect, and then it attenuates off towards the edges and the corners. Now if we rotate this, maybe we can see something. I don't know if you notice here, but you can see a little bit of funkiness with the lighting there. That's an artifact of the per vertex lighting. A little bit of nastiness there. But overall, it looks pretty good. It's looking a lot better than it looked before anyways. But this comes at a cost, right? Because by increasing the tessellation by 16, that means 16 more in the X, 16 more in the Y, you're increasing the geometry complexity by a factor of like 250. And even then, we could see some weirdness with the lighting. Now, there's a common theme. There are many common themes and threads running through this series. And one of those common themes is breaking things down to smaller levels of granularity when you find a problem. Like, for example, when we had the problem of composing objects in a scene, I told you maybe we could sort them by object, but no, some objects could be interpenetrating each other. And then I said, well, what if we sorted them by triangle? But even triangles can interpenetrate each other. So what's the next smallest thing? Sort by pixel, and there's where we came up with our Z buffer. Well, we can do the same idea for our shader. Instead of shading at the level of the vertex, what if we did the lighting calculation at the level of the pixel? So instead of calculating the colors at the vertices here and then blending it, what you're gonna do is at every pixel that you render, you're gonna use the normal at that pixel, and you're gonna calculate your angle and your distance, and you're gonna get your color for every pixel is gonna do the color calculation. So instead of doing 2 color calculations and blending, you're gonna do a separate color calculation for every pixel. That's the idea of per pixel lighting. Now, in this situation, it's easy. The normal is always going to be pointing in the same, it's a plane, so all the normals point in the same direction. But what if you're not going with a plane? So let's say you're rendering this object. It is ostensibly round, but of course it's made up of polygons here. And you've got the normals at the vertices pointing out where they would be if it were a perfectly round object. And you've got your lighting. So what are you going to do? Well, you're going to be drawing it. You're going to go for all of these pixels here. You are going to draw a line from the light source to the pixel that you're rendering. You're going to take the angle between the normal, the vertex normal, and that light line. And you're going to also take the distance. You're going to calculate the color here. But what do you do for this pixel here? What do you do for this pixel here? You have the normal for this pixel here. You have the normal for this one, but you don't have any of the normals for the ones in between. How do you do? What do you think you do? It's quite obvious, maybe. What you do is you interpolate the normals. So now, in a vertex shader, we were interpolating color across the surface of our triangle. Now, we are going to interpolate normals and use those interpolated normals to calculate our color at every pixel. And this will give us the correct result for a plane. But not only that, it's going to make these surfaces look nicer. And you can have less geometry and have smoother looking surfaces if you interpolate normals instead of interpolating colors. You're going to get a result that is closer to the ideal. So let's take a look at the code for that. I added a new effect, the Phong point effect. Although it's probably not technically a Phong shader. I'm going to call it that anyways. Phong point effect, per pixel point effect. So what are we going to be doing? Well, first of all, the thing we notice is that the vertex type that we're going to be using here, we have got to change it. We've got to define it so that it will incorporate some stuff into the calculations for the adding, the subtracting, and so forth. Because there's going to be a lot of things that are being interpolated. So we're going to have to interpolate the normal. And of course, we're going to interpolate the position. We always interpolate the position. We're also now interpolating the normal. And we're interpolating the world position. Now, this is important because the position and the world position aren't actually the same. The position is going to get all messed up with stuff for projection. It's going to get all mangled up when it hits the pixel shader. We want an unmangled, pristine world position, not something that's been translated into screen coordinates and it's all blown out of proportion. So we add a separate attribute to just store the pure world position, and this guy is not going to be subject to all the bullshit that the normal position gets. So we set up our vertex so that it will be able to interpolate these 3 attributes. And then let me find the vertex shader. And then we do the calculation for the world position. We put that in position and in the world position attributes. So the same value is going in these 2 attributes, but they will be treated differently in the pipeline, remember, because this one is going to get all messed up by the screen transformer. This one is going to remain the same. And for the normal, we only want to apply rotation. We don't want to translate a normal because that's going to stretch it the mother trucking out. We don't want stretched normals. We want nice, tight, puckered normals. That's the ones we like. Anyways, so vertex shader, pretty damn simple. Next, pixel shader. This is going to get the input And we are going to have our world position, and we're going to have our normal. This is going to be pretty much identical to Gouraud shading. We calculate a vector from the pixel that we're drawing to the light source. We get the length of that vector. We get the direction of that vector. We calculate the attenuation using the length. Then we do all the multiplication stuff with the attenuation and the light strength and the angle between the vectors, the normal and the light vector. And then we combine the ambient light with the diffuse, saturate that stuff, and there you go, you're done. That's all there is to it. In the Phong point scene, I don't think there's really anything amazing in here. It's pretty much going to be the same as the Gouraud point scene. There's nothing really that changes. Then in game.cpp, we add the scene to our list of scenes with a plane. And I've also tessellated this plane. I don't really want to do that, but we'll fix that up when we actually run the tests. Let's look at the last commit for this video, and that is I just added a Suzanne version of that scene. So you've got a little more detailed model testing out our Phong point scene. Now let's check this code out for a little while. So first off, I want to compare. I don't like this comparison. The whole point of doing the per pixel lighting was so that we didn't have to tessellate. So let's bring it back down to the default tessellation, which is probably like 2 or maybe 1, I don't know. I don't know how I counted it out. So we'll do that, and let's run this for now. So here it is with only 2 triangles, and we're running per pixel lighting on this mother. And if we rotate it, look at this. No funkiness on the edges here. This is the tessellated Vertex one. You can see a lot of funkiness on these edges. No funkiness whatsoever. This is again the per pixel. Much more beautiful. And here's what the point lighting looks like on our familiar Suzanne model. And I think if you compare this with what we had before, you will agree it's a lot more detailed. You're going to see smoother lighting gradations and a lot less geometry artifacting here. It's going to look smoother. It's going to look nicer. Now, looking at this, you might say, well, Chili, why do we even bother with vertex lighting then if pixel lighting is so much sexier? Well, first off, pixel lighting, doing those lighting calculations, one for every pixel is generally going to be more expensive. It's going to cost you more GPU power to do that. So what you often see is a little bit of a trade-off between quality and performance. So here's just some information from Unity, and it's how they render dynamic lights in a scene. And apparently, depending on the quality level that you put the game in, it's going to say, well, in the fast and fastest, there are no pixel lights. All lights will be vertex lights. As you increase the quality, you'll have more and more pixel lights in the scene. So it's going to take for example, if you're in beautiful, it's going to take the 3 most important lights, probably the 3 closest ones, and it's going to render them using a per pixel shader, and it's going to render the rest of the lights using a per vertex shader. So it's important to know both of these techniques because they're both commonly used, often together in the same scene. Now, one last little topic I want to talk about here is normal mapping. You may have heard of the term normal map, and the way it works is, well, it's the same idea as a texture map. A texture map allows you to apply some very high detail color information to a low detail geometry. And what a normal map allows you to do is to apply high detail normal information to a low detail geometry. So for example, let's say you've got this cube here. It's just flat cube. If you interpolate the normals at these things, you're just going to get a flat surface. But if you can apply a texture to it, and that texture will tell you the normal at any point on this, then you can give it any kind of normal pattern you want on there, and then you're going to get different kinds of shading. It's going to look textured. The thing that we call a texture map should really be called a color map, and the thing that we call a normal map, maybe we should call that a texture map, because as you can see, it adds texture to a surface. So take a look at this model here. It's modeled with like 6 million polygons. And using that level of polygons, you can get a lot of high detail, a lot of wrinkles and stuff. But you can't use 6 million polygon models in a game. So you've got to take that down to something more reasonable, like 6,000 polygons. When you do that, you're going to lose all that high resolution, all that high frequency wrinkle information. What you can do is you can take this low polygon model and you can apply to it a normal map that will map normals of all those different nooks and crannies onto this low detail polygon model, and it'll look a lot similar to the high polygon model. So normal map allows you to have your cake and eat it too. You can have these fine shading details, but you can have the performance of a low polygon model. Now, normal mapping it's a little bit of an involved topic, so I'm not going to go into it in 3D fundamentals. We're going to cover that in hardware 3D. But I just wanted to mention it here because it is relevant to the idea of per pixel shading. Again, to summarize, basically, instead of getting your normal information from your vertices and interpolating it, you are instead taking the normal information from a separate texture map. And those normal maps generally look like this. One final thing before I leave you today. This code that I wrote here, afterwards I realized there's a little bit of a bug in it. Can you spot the bug in this per pixel shader code? You should pause the video right here if you want to figure it out for yourself. But the answer is, it is right here. This, using the normal directly like this, is not going to give you the correct result in most situations. It's going to be close in most situations, but it's going to be a little bit off. So again, take the situation of we're rendering this, we'll call this a triangle. We're rendering this triangle right now, and we're interpolating between these vertex normals. So what is the interpolation between these vertex normals, say, at this point here? Well, we take the normal like this, and we take another normal like this, and we interpolate them. The interpolation is going to be something like this, halfway in between these two guys. Now, what's the problem here? Well, the problem is this guy's length is 1, this guy's length is 1, but our interpolated normal, its length is going to be less than 1. So let's say this guy's length is 0.75. Then when we do the dot product of our quote-unquote normal with the light normal, we're actually going to be attenuating by an additional 0.75. We're losing intensity because we haven't actually normalized this guy back to his unit length. So what we should be doing in here is we should be doing in.n.getNormalized. And that'll give you the correct result. Now, if you do this, you're probably not going to, realize, or you're not going to recognize a large difference, because with a fairly detailed model, the difference in angle between adjacent normals isn't going to be that great. So your loss here is going to be small. But in very sharp corners, it will be noticeable. So you got to make sure you renormalize that interpolated normal. And that's going to about do it for today. Stay tuned for the next video. We're going to do something interesting. It's going to be fun. It's going to be very sexy. We're going to add some glossiness to our rendered models. But until then, thanks for watching. I hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more 3D fundamentals.